I'm Francis Manzella. We have a crew of distinguished panelists here, including Jeff Madison from RPG, Lars Tofastrud, who works with me and is also a partner in Griffin Audio, Wes Lachaux from Wes Lachaux Designs, and what's your name again, sir?
Oh no,
Chris Polonis from Polonis Acoustics and Sound.
sorry.
None of us had lunch yet. We've been busting trying to get this set up this morning, so we're a little bit punchy. Bear with us. We do actually, I have it all mapped out here. Everything we're going to talk about. We're going to talk about a couple of, 2 or 3 different measuring systems that we use to try to do that voodoo that we do so well. Then hopefully what we'll do is talk a little bit about what we do after we see this stuff on these measurements and what it means to us. I'm going to wrap it up at the end, and we're going to try to leave a lot of time for Q&A at the end. So make yourself some notes if you have some pressing question that comes up that you won't be able to remember for 40 minutes, and then ask us at the end if you can, please. We're going to start with Wes. Wes is going to talk a little bit about, take it away, Wes.
I'm going to start with, hi, I'm Wes Lachaux. I'd like to talk just a little bit about what the type of software that many of us in this business use. There are a lot of the original software was actually a hardware device called the TEF device made by Crown. The concepts, the original units were a guy named Richard Heiser invented this concept back in the Stone Age, and has to do with being able to actually measure real rooms. Before this software came along, most acoustic measurements had to be made in anechoic chambers, which was completely impractical for trying to measure something like a control room or a real acoustic space. I'll speak up a little more. It's so dead in here. Yeah, what's the deal? But the idea, the reason it was so tough back in the day before this type of software was that the room interaction was so severe that any measurements that you took, it was just gobbledygook between all the reflections coming back into the microphone and so on. So anechoic chambers, to some degree, got rid of all those reflections, but then how do you measure a real room? Well, the concept of TEF stands for time, energy, frequency. There's some other types of software. There's ETF, which is energy, time, frequency. And then there's several other types, SMART, Melissa, and so on. They all basically do the same thing. They take the time domain into account, whereas what you may be more familiar with an RTA type thing, real-time analyzer, which is just energy and frequency. You've got the frequency starting from 20 to 20K, and you've got a graph basically that shows peaks and valleys of energy. When you start to bring, now this particular graph I've got up right here is actually the 2 other dimension, well, the dimension of time against the dimension of magnitude or energy. The thing about a 2-dimensional graph is you've got to choose. The software devices pretty much will allow you to look at any 2 dimensions that you want. You can look at energy and time, energy and frequency, or frequency and time. Like I say, most people are most familiar with the two dimensions of energy and frequency. But this particular graph right here is showing, and then some of you may have seen waterfall graphs that show all 3, but I'm not going to talk about those. I'm going to talk about 2 dimensions at a time and why you might look at these 2 dimensions. When you're looking at energy is the vertical dimension and time as the horizontal dimension there. This is obviously, we're not looking at frequency, so this is energy at all frequencies, okay? What you're seeing right there is you see a very severe peak on the left. That's the original signal. This was a measurement that I took in a control room. Somebody asked me to come and test their control room because they had some severe problems. So these tests we took in order to show various things about the room. You'll notice that maybe about 2 or 3 milliseconds after the original signal, see the secondary peak, it's almost as loud. I'd say it's about 3 dB down from the original. That is the reflection of the console. And we know it's the reflection of the console. If it's about 2 milliseconds later, you can take measurements of the surrounding surfaces. The walls were too far away. It would have been at least 7, 8, 9 milliseconds, the floor, ceiling, and so on. That was the console reflection. If you have any doubt that console reflections are a problem, just take a look at that graph. Basically, what you're hearing is a secondary mix coming at you only 3 dB down a couple milliseconds later, and imagine what that does to your frequency response. Yes, sir.
Just one question. You said that the first peak, just to clarify, that's the impulse response?
That's the original. This was done. Yes, that was the exciting sweep. And then right after that, at 2 or 3 milliseconds later, you've got, that's how, well, especially because this particular, the console was a hard surface, and it's right there. It's the path length, it's about 1 foot per millisecond is what you can figure. And so if you've got, you can just measure with a tape measure the path lengths from the speaker to the microphone. And if you've got a ceiling that's up, 5, 6 feet, it's probably going to add about, 5 feet or so to the path length. And you can see some other peaks on here that have to do with the back wall and so on. You can see there's one around 10 or 12 milliseconds there that's most certainly the back wall, and this is a very small control room.
Let me interject one thing also, because if you guys haven't seen this before, the reason that you don't see that first peak right away is that's the time it takes the sound to travel from the speaker to the microphone.
Correct.
So this is from this black line.
That's when the sound was generated. That's when it got to the microphone.
That's exactly right.
And that's when it bounced off something very hard.
Very hard.
Back at the microphone.
So hard, and that it now you can soften the walls and get that to go down some, but you should know that that's how loud reflections can be. That's how important it is to get rid of reflections. We prefer to get rid of reflections with geometry. With better speaker positioning, we showed this to the engineers in the studio to prove to them that they really needed to get their speakers off of the meter bridge and to move them back so that they didn't get that direct bounce off it. Now, I want to go to this. This is the same room. Click. Okay. This is what, you see the comb filtering there towards the right? That's called comb filtering, where you've got these incredibly sharp peaks and valleys. That's the frequency response caused by that reflection that comes a couple milliseconds later. It's horrendous. It's the swings are, imagine trying to EQ something, when actually that's what you're monitoring. And you know that there's something funny going on around 4K, but, try to figure out what it is. That's your monitoring situation. That can be alleviated by getting rid of those reflections. So this is, now we're looking, of course, at 2 other dimensions. We're looking at, instead of the dimension of energy and time, we're looking at the dimension of energy and frequency. These can be transformed back and forth by using the Fourier transform function, which is a mathematical function. But you could sit and tediously do the math yourself if you wanted to and had enough time. But that's what the TEF computer does for you, and other types of computer software makes that really easy to do. So anyway, and then I didn't bring any, the other 2 dimensions. You could be looking at frequency versus time. And that's pretty much all I wanted to just give a sort of an introduction to the software and then pass it over to Lars.
Yeah, Lars is going to talk a little bit more about TEF if he can stop making all the stuff go off the screen.
Just bump the upper right corner of the screen.
That is a different ETC curve. It's the same typograph that Wes was showing us. That's also showing the initial time it takes for the sound to arrive at the microphone. And you can see the horizontal scale is longer in time. So we see more of the room decay. Mm-hmm. We see that there is a relatively flat area in here of reflections, and that's before the reflection reaches the back wall. And we know that diffusers, like we do here, we place a lot of diffusers on the back walls, and we want some return from the rear wall, because we don't want to make the room completely dead. It needs to be somewhat natural to be in the room. But we do not, like Wes said, we don't want any reflections really, of significance in here, in this very early area, because it affects the frequency response of what we're actually hearing. And when we get past the point of the rear wall, the reflection or the sound has traveled around in the room so many times that the energy starts to go down, it decays. And even if you don't have a real RT60 in a room, we do want to look at how quickly the sound decays at a lot of frequencies. And Chris Polonis will show you the waterfall plot and how we look at, how we place all the time and the frequency and the energy in one graph. All this again is just showing one or two dimensions. Wes indicated how two closely spaced sources will interfere with the frequency response. It creates a comb filtering. So that is one of the aspects that is bad with these early reflections, that it destroys the frequency or response of your loudspeaker. There are other aspects which it's not really that visible on this graph, is it?
Yeah, it's a little hard to see the yellow lines, but there are some contour lines above the above the peaks and valleys there.
Maybe I should go up there and point at it, if that's possible. Sure. There was this guy called Haas that came or did lots of research on this reflection issue. And he had one guy sit down with a speaker in front of him and one speaker out to the side, and they delayed the time and the level on that one speaker until it created these three different effects. Where it was inaudible, there's a line that maybe some of you will be able to see here. And they concluded that if the reflections are below that line in relationship to the direct sound, then you won't really hear it. If you get above this line, there's another line up here. I don't know. Can you guys in the back there see that at all?
I can barely see it yet.
Yeah. And if you have reflection that goes into that area, it will add spaciousness to our sound, or what is produced by the speaker. And in a control room, you don't really need or want that until you are beyond 20, 30 milliseconds. Then you have a little bit of spaciousness, but it doesn't interfere too much with frequency response of your loudspeakers. In a performance space, in a recording studio, you do need these, but not in a control room. There's two very different things. The place where you reproduce things over a set of loudspeakers and where you actually have musicians. Because if you do have reflections in here where you actually play an instrument, that adds to the richness and spaciousness of the instrument. If we have reflections that are above this line, and like we saw on Wes's graph, we had one that was basically up here in relationship to the direct sound, then there's a series of things that happens. One of them was the frequency response starts to go like that. Another one is that imaging completely falls apart on what we're listening to. And you'll find that certain tones on the guitar, for example, can move off to the side. You have all kinds of weird things that start to happen. And there's one line also all the way up here. And if we have signals or reflections that comes out to our ears that are above this line, then they are discrete echoes. You'll really screw everything up. And of course that's difficult to do in a recording studio, with speakers. But in performance spaces, or parking structures, you can actually find that reflection comes back at you that are actually above this level, and you will hear the decay or the actual echo. So this is, this is all the same subject, really. but there is very complex interactions between what makes a difference in the frequency response or what makes a difference in our perception of the sound. While the variations in frequency response, they might not be that audible unless we move a lot and we actually hear the wah, 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 wah from the filtering effect, comb filtering effect. But these effects with spaciousness, image effects of the shifting and spreading of the image are other issues. And we have to deal with those also. And like Wes said, when we design a control room, we deal with those in geometry, basically, in the room, and treatment like here. Like, try to get rid of the first reflections. Of course, like some places, you actually do need a console in front of you, and then you need to make sure that you don't have these very short reflections off of the control surface that you use. I don't know if there is anything.
No, I think that leads very nicely into Jeff talking about what it is we try to do on the back wall a lot of the time, and that's what we're going to get to next. Is Jeff's going to talk a little bit. So far, this is going great. I haven't
come around here. I think what we're really talking about right now is we're talking about small rooms. Everybody here is pretty much involved in a small room in a controlled environment where you're mixing, recording and mixing and mastering and doing things like that. And we're talking about reflections. We're talking about the fact that we're taking very capable sound-producing devices, loudspeaker systems, full frequency range, and we're pumping sound into a small room, and there's all of these surfaces around the room that are going to play a role in ultimately what you hear at your position. There's the ceiling, there's the floor, there's a console if it's in front of you, side walls and a back wall. Depending on the geometry of the room, there's usually at least those. So there's a lot of, it's a very long topic to really get into room design and everything that can go into that. But there's three main components that, in coming to a panel like this and talking about being able to measure your room, learning about what that means, and being able to treat your room. There's some general concepts I think that you could leave with that you could all apply in your own spaces. And there's treatments, which we'll talk about today, that you can consider. But there's what I'd like to talk about is really what not are the treatments, but what do you expect from something that's going to affect the sound that you put in your room. There's three ways you can affect the sound in your control room. Does anybody know what those three ways are? There's three ways that a surface can affect the sound. Mr. Manzella.
Diffusion, absorption, and reflection.
Reflection. So within reflection, I would include the ability of redirecting the sound. You can use a reflection smartly to just use it to change the direction of the sound and maybe get it away from your listening position. So you have these three things. Reflection is pretty simple. You've got effectively a flat surface. Absorption, I think people are most familiar with. That's something that tends to be sort of squishy and fibrous. There's foam, there's fiberglass, there's cotton batting, and there's ways of sort of tuning those things to be able to absorb in different frequency ranges. For example, if you wanted to focus on low frequency absorption. Low frequency absorption separates out from higher frequency absorption because the sound waves are so large that devices like foam and fiberglass and stuff, it becomes incapable of really being able to affect it without some smart manipulation of it. And then there's sound diffusion, which I wanted to talk about, aside from the fact that I'm from RPG and we specialize in sound diffusion. I wanted to talk about because I feel like from my position, I see a lot of confusion in diffusion. In fact,
diffusion, confusion.
There's people that have called it, jokingly, colleagues of ours that are on other camps that call it confusion when we talk about diffusion. And I don't really think it's that confusing. Actually, I think the market has made it confusing, and so I want to just give you a couple things to think about that you can use, information you can use to determine, your feelings on the topic. A sound diffuser is something that scatters sound. It doesn't tend to absorb it. It doesn't just change the direction of it. It's kind of like throwing your champagne glass at a brick wall and it breaks out into a bunch of little pieces in all sorts of different directions. It's effectively what it's doing to the sound. It's breaking it up into smaller reflections, ideally that are going over a wide area, a hemisphere coming off of the surface. So what does it take to be able to do that? Well, what the research shows it takes very particular phase relationships of a surface topology, whether it's curved or stepped, like something like that, or whether it's pocketed, like the units on the back wall. You've seen all sorts of different shapes and sizes, but the important thing is that there's a way of quantifying what exactly that surface is doing, and it's called a diffusion coefficient. The diffusion coefficient very specifically tells you the quality of how that sound is scattering off a surface. It's a metric, like we have an absorption coefficient. It tells you how much of the energy that might approach a soft surface, how much of it is going to get absorbed and converted into heat, and how much of it is going to fight its way through that to the wall and still make it back out. So if something has an absorption coefficient of 0.5, 50% of that energy is going to get converted into heat, and 50% of it is going to find its way back off that surface and come back into the room in the same direction that it approached it. So a diffusion coefficient is really something when you work with a designer or you're working on your own rooms and doing it yourself. If you're looking at diffusion, you want to make sure that something has a diffusion coefficient because that tells you exactly what it's doing to the sound. Now, there's other coefficients on the market that I think have confused things over the last couple of years. And it is confusing without really delving into it if you look at it, because we have something called a scattering coefficient. And the scattering coefficient came about because we have computer modeling software that will tell you for large spaces like churches and conference halls and stuff like that. They allow you to model a space and try to help you predict what a space is going to do before you build it. So you can kind of build it up and get a good idea of what your reverberation time is going to be and things like that. That software, we want that software to be able to utilize a diffuse surface so that you can tell the program if that surface is reflective, absorptive, or if it maybe is going to scatter the sound. But all the better that software can do right now is to be able to tell it, say, this surface is a diffuse surface, so it's going to change. We're going to say it's going to change the direction of the sound. So a scattering coefficient basically gives you a 0 or a 1. So if a unit has a scattering coefficient of 0.9, that means 9 times out of 10 in a computer modeling program, when sound strikes that surface, the computer is going to decide in a random way that it's just going to change the direction of that sound, which sort of helps you model what you might be getting out of using diffusion in a large space. So the scattering coefficient really, in terms of what it's doing in your small room, is virtually useless. And I think there's a little bit of confusion out there on that it doesn't tell you anything about the quality of the sound. Something shaped like a triangle is going to have a very good scattering coefficient because it is going to change the direction of the sound.
10 out of 10, right?
10 out of 10 times. However, it's not going to change the temporal nature of the sound, and it's always going to be going in one direction. So a diffusion coefficient for a triangle is actually going to look pretty bad. So you really want to I think that's good knowledge for you to have, is to just understand, you're constantly looking at specifications, microphones, your speakers, your amplifiers, your preamps, everything. You want to know, you're putting sound into that, what is it doing to it as it's putting it out? So you're throwing sound at something in your room, what is that thing doing? So I think the specifications are really important, and the diffusion coefficient tells you. It gives you a bandwidth of what frequency bandwidth that's effective, and how well it's actually diffusing. So that's important. And the last thing I want to talk about is the fact that there is advancement, and this is sort of, I'm a little bit ahead of where the publications are coming out, but there's a concept of a diffusion array coefficient. There is an effect of when usually test a device, you test one, maybe 1, 2, or 3 devices. When you put a piece, like if you take any one of these pieces and you measure it for a diffusion coefficient, it will give you a certain piece of information. If you measure 2 of them, that is going to be a little bit different. 3 of them, 4 of them, 4 on top of 4 of them, 4 on top of another 2 of them. So as you develop something into an array, which is very often what you do on the rear of a control room when you're using diffusion, that affects, the way that those are put together affects the diffusion coefficient.
Easy.
So there is a work in progress right now to develop diffusion array coefficients. To just give you an example of what that means, there are things like barrels you see a lot. They're just a polycylindrical device. You can use wood. You can bend them to break up reflections. You can buy them molded. It's just a simple curve at some height. Those are actually tested for a diffusion coefficient. Those are pretty good because you have a constant difference in time and angle of scattering. It doesn't really affect the time as much as you would like for a diffuser to, but it actually scatters the sound very well. When you put one next to the other, what happens when you put a 10-inch driver next to a 10-inch driver and play sound through it? You get some kind of lobing. You get some kind of lobing in between. When you add 2 more of those and you have 4 of them, you start to develop some kind of pattern of lobing. The same thing happens with these devices. So something that is symmetrical and arraying it in a periodic manner actually degrades. If you have 1 barrel and you test 6, the diffusion coefficient drops from a nice high number down to about next to nothing, because the quality of that sound now coming off the surface has been tainted. You might be getting very beamy, low Q, high Q, very low Q beams coming off the in between the high Q. Thanks, Chris. I'm going to stick with beam. I'm going to stick with beaming. Okay, we haven't had lunch yet, so my Q is off.
Want some cashews?
I'm low Q. So that's something to consider, because you might read somewhere to say, an ARC does a nice job, but as soon as you put 4 or 5 of them behind your listening position, it starts causing problems and actually turns it into just about as bad a surface as just having a flat wall, which is a pretty bad surface for a reflection coming back. So I just think that's information that you can really use, in addressing your own needs to sort of smartly research it and know what to expect and know what to look for. I think that's it for me.
Cool.
Great, Jeff.
Thank you, Jeff.
Thanks.
We're going to move on to Chris, who's going to talk about something completely different.
And the same.
Exactly, like I said.
Exactly the same, only different. Great. Thanks for coming out. We got a nice full, this is great. You guys are here. SMART is another program that's kind of does a lot of things in one package, which is why I tend to like it. It will do just a standard RTA, like you've all seen, up to 24 points per octave, all the way down to single octave measurements. It's kind of a 2-part software device. You can take an impulse response in what's called SMART Live and put it into acoustic tools, and it'll give you acoustical information like what we've been talking about here, where you see your energy time curves, your decay response, and then it'll put it into a 2-dimensional color graph, which will tell you, and I'm going to show you some of these in a minute, how long certain frequencies are lasting in a room, how much energy of that particular frequency is sustaining in that room, and that will affect a lot of aspects of your listening experience, whether you're in a control room or a live room. And I have a couple of graphs that are here that are kind of fun and pretty radical. Another thing that it will do is it'll measure your noise criteria. That's important to us when we're doing, and it should be important to you too. If you're going to have a recording space, for example, you want to know how loud your air conditioning is. What is an NC curve? And maybe I'll start with that, and because it's kind of dry, and then we'll get into more fun stuff in a minute. But can you guys see that? Okay?
Oh, sorry, Chris, time's up. No, just kidding.
That's okay. This is what an NC curve looks like, and if you'll notice, that there's no measurement below 63 hertz. So when someone says I have an NC10, you could also have, down at 30 hertz or 20 hertz, you could have an incredibly high reading, and it's still going to maintain that noise criteria is low. So a lot of times, if you're involved in building a studio or you want to look at an NC curve, I like to put a limit on the NC curve. So I modify the NC curve to say NC20 limited to 35 decibels or something. So no frequency can go higher than a particular frequency. Now we had a little problem on a project actually. This man in the back here, we were doing a facility for his company at Sony, and we had a strange little occurrence with the HVAC, and it was all looking pretty good here, and then we had this pop up, and it got us up to an NC, what does that say, 24?
25.
24, yeah. Right there at 125 hertz. And then it kind of looks okay back here. So there was just something that was vibrating that was causing this to occur. So SMART allows these graphs to overlay over your frequency response so you can measure your noise. Of course, you put a microphone and you calibrate and whatnot. I think it's just important to recognize that you still have 48 dB on an NC15. 63 hertz is still pretty loud. So that's louder than you really want. And therefore, it's a tool that's useful to some degree, but without understanding what it really is and knowing that you don't want to see, for example,
What does NC stand for?
Noise criteria. Okay, so enough about that. Now, here's how SMART also does these impulse responses. You can see here's the initial excitement, and then this is a control room. You can see it's pretty well controlled. It drops down pretty fast, and there's a couple of reflections down here. They're not really interfering with anything to speak of. So that's what the SMART impulse response looks like when it's taken into acoustic tools. Or SMART 6 now actually provides for that. So what we can also do with this impulse response is we can put it into what's called a spectrograph. Now this is kind of a funny little graph here. I was hired to validate that a parking structure in a casino would be a likely candidate for an installation company that was trying to sell them a whole bunch of speakers.
Can't hear.
Sorry?
Can't hear.
Can't hear? Okay.
Speak up, pal.
Sorry. So what they were trying to do was explain to the company that by putting all these speakers in the parking structure, it was going to be okay. I kind of suggested that they might not want to hire me because I'd have to tell them the truth. Well, what we've got here is a 30 dB reduction, and you can see there's quite a lot of energy still hanging out here. If I looked at a decay time of RT60, which takes it down 60 dB, this would just keep going. These reflections in particular down here in the lower frequency here, it gets okay here. There's not a whole bunch of energy happening. And then all the way from about, I guess that's about 2K up to around 8 to 10K, there's a lot of energy happening here. And what that relates to is how the frequency response and the intelligibility. Now, this is a speaker that's really not too flat or not too bad. It's a reasonable speaker, but here's what it looks like in this structure as a result of. Okay, now you can see here you got this range down here in the 100 hertz to a couple hundred hertz, and if you compare that to the decay time, well, look at what happens down here. See all this red stuff? That's loud. That's loud, heavy energy, and it's affecting. And then you can see here, as we get up into the mid bass, well, that's where it starts to clean up in the decay time. And look at there, And so it really does. That energy affects the amplitude. That amount of energy, and it's picture perfect in this particular graph. And how that works on intelligibility is pretty poor. This is the stuff they didn't want to see. If you look at some of the frequencies were actually near. This is 2K. Here's your intelligibility. And we had a little discussion earlier about what is intelligibility. Does everybody kind of understand what that means? It's self-explanatory, but how much of the information that you're getting is reliable information. So it's not very good here at, what are we at, 2K, I think? Yeah, or 2K there. I've got another one down here. 400 looks really good, doesn't it? Look at that. It didn't even register. It was that bad. And I'm showing you these graphs because these are really bad. I wanted to give you examples of how to measure those. So you kind of get the idea on that how frequency response is affected by decay time. Does that all make sense to everybody? You got all this energy in the room at a particular frequency. You might have a perfectly flat speaker, and that's where all this treatment really comes in handy. If you've got a whole bunch of 3K bouncing off or 1K or whatever off the drywall, a perfectly flat speaker out in the room is going to measure louder in amplitude at those particular frequencies because of that. So these treatments and these measurements are really important tools for all of our joy and ease in this business. Now what I'm going to show you is how, when you're measuring a speaker in a room, this is this is a studio that I did up in San Francisco at the listening position. You can see this is your phase. This is how SMART measures your phase response versus your frequency response. This is the transfer function. What I think is pretty interesting about the transfer function. Hello. Okay. The transfer function, the best, probably the easiest way to describe it is it's taking the information that's being sent to the speaker, and it's comparing it to the information that's being received by the microphone, and it's telling you what the difference is, and therefore it gives you a very accurate comparison. Hence the frequency response. So. When we're doing speaker measurement, control room, and whatnot, it's important. I do have a very cool thing I'm going to show you here in a minute. Let's see here. Okay, this graph shows. I had a client who was moving his studio, and he had a pretty decent set of speakers in there that had a pretty nice response. That would be the pink graph. Can you guys see that pink graph? Okay.
So they could drop the lights a little bit.
Yeah, you want to fade those down a little bit, maybe. There we go. Much better. So what I did was I took a very close reading of his speaker from about 1 meter, and at that point there wasn't a whole bunch of interference from the room. He had a fairly well treated, at least in the mid and high frequencies. And you can see it's a pretty smooth graph. The phase response looks pretty smooth, and that little hiccup in the middle of the phase response, that's actually not so bad. That's a 360-degree turn, so it's in relative phase, and it was a pretty good response. You can see it reflects okay in the mid-range frequency response. Then I pulled back about 8 feet, and you can see it all starts to fall apart. And in particular, you take a look at the low frequency, you can see all the nodes starting to really interact with the response. So depending on where you are, those things will change because there was not very much low frequency control. And as you move around in the room, those low frequency bumps and valleys are gonna change depending on where you are.
So that's the blue line?
That would be the blue line, right. So ultimately what you want to see is as close to your anechoic response as possible in the far field. And that's a pretty good example of how a room that had reasonably good high frequency control, which is the easiest thing to do, and you can see it start to fall apart pretty good as we get down into the low frequency. Any questions?
We're going to get to that.
You mentioned about calibrating the microphone, because obviously, does that program, does it come with a calibration microphone, or is there a calibration?
No, it doesn't, actually. So
It's one difference between the TEF and pretty much all these other software packages is that the TEF actually is calibrated. When it says 70 dB on the graph, that's what it is, while it's all relative decibels on most of these other packages.
right.
You can calibrate it though if you have an additional
Yeah,
device.
yeah. There's a little, for a couple $100, you can get a Larson Davis calibrator that will give you a reliable calibration. And normally, to tell you the truth, for most of what I'm doing, I don't calibrate because it doesn't really matter. I just have to be close. If I'm measuring something where somebody's going to be in trouble, like an HVAC contractor who didn't put the silencers in, then I have to calibrate and go to town. Here's another showing of how the reverb or the RTA looks on Smart. Looks just like most RTAs you've seen. This is a 3rd octave scale. It goes up to 24 octaves, and it'll show you your left is the orange and the green is the right. Or the left is, you can compare them, that's what I'm trying to say. How's that? One more thing I'll show you. Smart does a pretty good job. This is about where it kind of stops working on the low frequency, down here around 7-8 hertz. And this is a really big 18-inch subwoofer. This was taken at the listening position of his studio, actually. So it'll give you a reasonably decent low frequency response. It shows you your phase versus frequency there. Again, these are just a bunch of different readings and graphs for different purposes, looking for noise, etc. Speaker analysis. That pretty much, I think, sums up Smart. This is a pretty good graph. You want to see things that look like that. Yeah, that's good. Again, this is at a listening position. Pretty well controlled, lots of good absorption diffusion in the right places, and that's kind of the goal of getting these measurements, using all the information that we're all giving you about treatments that you can purchase, some that you might try to build yourself, careful, and getting somebody to help you or get good books and really study up before you start putting up walls, because it's real expensive.
I'm going to tell you guys, that's a spectacular measurement for a speaker in a room 7 feet away from the microphone. That's spectacular. We don't,
Plus or minus 3.
Thank you.
Can't expect to get plus or minus 3.
Now this is actually the thing about this. This is a speaker that uses DSP, so I'm able to really control what's happening in the digital domain.
That's a really spectacular measurement of what DSP can do for your speakers in a room.
I'm working on getting a passive speaker to look like that, and we're getting there. But anyways, thanks, Fran.
Could you explain just?
Sorry? Oh, that speaker, that would be my 15-inch wideband. It's a single 15 with a super tweeter. I'm only measuring on Smart. On the new Smart, you can measure up higher because it's higher bit rate. This was a previous version that only had 48K. But this speaker would go out to 40 kilohertz as well.
Before you leave this, though, could you just briefly explain what the phase consequences are? It goes from plus 180 to minus.
Well, that's what you call trailing phase, and it's really sort of what you want to see in a speaker. You want to see a gradual trailing phase. It tends to be more natural. If you get a perfectly flat response, no one's going to argue with that. But that's sort of a whole nother forum about how to replicate realistic sound and through the loudspeakers.
I think, guys, Lars can tell you better about this than me, but the phase is directly tied to the frequency. They're inseparable. So you see anomalies in the frequency response, you will see anomalies in the phase response. You can't take the two apart. They're two representations of the same thing. All you really want to do is not see big hiccups in the phase. They're generally representing some kind of an acoustic problem. They could represent an electronic problem or a physical problem with the speaker, but what we see most often is you see a big hiccup in the phase, it's directly tied to a reflection or something like this. So phase is just another way to look at the same thing. And it's a really good indicator when you see one of these things that something's going on when you see that in the phase. Go ahead.
There's one way of disconnecting the frequency and the phase response, and that is with so-called FIR filters in DSP. So what you do then to correct the phase response is that you have to insert a lot of delay. And in the studio, it's just not very useful because you will have 200 milliseconds of delay on your speakers. And it's not going to work. If a drummer has a 200 milliseconds delay on his, what he's hearing, it's just not going to work.
And
that is the only way.
Sorry, one thing, I kind of missed what you were getting at. If you're looking at this, we're basically somewhere in the middle of a wavelength as well, and that will cause an occurrence to where the phase is going to have difficulty measuring. Now, if I were to step back 40 feet, then this would all flatten out.
Right.
So you have that issue too. And what Lars is talking about is delaying everything, the tweeter and the super, delay that 30 or 40 feet to catch up with what's happening here so that you can get out of that lobe. But the bottom line is if you look at the frequency response here, it's not affecting your joy. This is really cool that you're able to hear that stuff way down. There's one other aspect. I know I'm out of time. I'm going long, but one other
We're out
thing.
of time about 10 minutes ago, pal.
All right, I'm done. There is a thing that SMART does which shows you coherence, and I'd have to run the pink noise and all that stuff to show you, but it basically gives you a graph of how much interference the room is giving you against your frequency response. And that's pretty cool because you can say, oh, wow, I've got there's something happening here at 3K, and the coherence is really weak as well, which means there's a lot of room interactivity.
I think the coherence is kind of like what you were talking about with intelligibility. It's how accurate is the information at this frequency is what it is.
It really is, and SMART will show you that in real time.
Yep.
As right across the frequency response. It's right up here, right along the top of this would be a red line, and maybe where there's a little reflection or something happening here, you might see a little drop down as to alert you that it's probably the room. Okay. Sorry.
Plug back. It's okay. No worries. I think these guys are here to hear what we have to say. They might even stay an extra 10 minutes if they have to.
All right.
Maybe not.
So there's that.
So now the last thing that I want to show you guys before we get into a free-for-all with the Q&A is we've talked about a couple of different software packages today. We've talked about the TEF. We've talked about SMART. The TEF is actually can I just back up? I want to stand.
Do you want to switch?
No, it's okay. I want to show these guys what the TEF is. This is a TEF 20 preamp box. Okay, it's a hardware box that you buy, and then you buy the software that works with it. I probably got about between $3,000 and $4,000 tied up in TEF right now. Okay, the SMART software is the newest version. I believe
$1,200 with the acoustic
package. Tools. It's $1,200. Just the real-time package is about $750. So, these are all great tools, and they're probably really geared towards professional consultants who do this for a living. There are a ton of tools out there that you guys can get for free or for affordable costs, which is a good thing. It's a good thing, right? You guys can take this stuff home. You've probably already got a good quality microphone. You've probably already got something that's certainly equal to or better than my crappy little Edirol Firewire box here to get the stuff into and out of your computer. Be a little bit careful. Be very careful. A little bit of knowledge is a good thing, right? It's what do you do with these measurements once you have them? This is what we get paid money for, is to look at these measurements and figure out what to do with them. I'm all for encouraging people to make their own tests and get as much information going as they can. So what I want to talk about is one of the packages that's available for the Mac. Probably the main reason I bought this Mac is because of this fuzz measure software. And I just thought it was so cool, I had to go out and buy a Mac. I'm not a Mac guy, so bear with me. I'm becoming a Mac guy very slowly.
This is how we get you hooked.
Yeah.
We get you a little...
The first one's free, and mine wasn't free, though.
Something.
So, how many people know about fuzz measure? Wow. Okay, one. I heard about it on this forum that I host on acoustics, and somebody posted some measurements they've done, and I was like, whoa, those are awesome measurements. How'd you make those measurements? And they said, oh, with fuzz measure. I said, I got to get this. So I started looking for it. Oh, it's Mac only, of course. My office is all PCs. A lot of people in our design business are PCs. Chris is an exception. He's a Mac guy. But AutoCAD is a PC-only program. So whatever, we're very PC-centric. This program, with any standalone, reasonable quality audio interface, what do they call it? Core Audio. It works real good with the Core Audio interfaces. You just plug it in and it goes. Even I was able to figure it out. And basically, what I was going to show is I did these tests in this room before you all came in. The bottom is an impulse response. We've now looked at impulse responses about 4 times, so you ought to be up getting used to recognizing these things. There's the gap. Here's when the sound came out of the unit. Here's where the microphone picked it up. There's an early reflection right there. You'll see it one thing you will see it better on the TEF. I mean, for that $4,000, I better be able to see something better, right? So there's I can zoom very easily. There's the initial sound, and there's that early first reflection. Same thing we picked up on the fuzz measure very nicely. And up here is the frequency response that it transfer functions out of that immediately while I'm waiting. It keeps resetting the display for me. For some reason, I have no idea why. Because it's so inexpensive, you can't expect everything, can
You
you?
probably hit the button.
Yeah, it's my fault, I'm sure. But here's the frequency response that the fuzz measure software immediately convolves out of this impulse response. Actually, on the TEF, you have to do two tests. You have to do this impulse test, and then you have to do a series of frequency tests. So they're not. It's just the way the software is set up. You have to do two different sweeps. What are we hooked up to now? Are we hooked up to your stuff?
Oh yeah. If you're going to make these measurements, you got to get tools that you can rely on. You don't want to go buy some kind of lousy. I'm not going to name any brands. I'm being filmed.
But there are also cheap, if you're just going to do, some measurements in your home studio, you can get decent microphones for this kind of measurements for like $50.
You can.
Yeah.
They're not being caged.
Behringer has one. It works fine. You can't do noise measurements with it because the self noise is just way too high. But when you're playing 70, 80, 90 decibels out from your speakers, noise is an issue, and it's flat enough that you can use it for this kind of stuff. When you buy an Earthworks or a B&K for several $1,000s, they're going to have a completely different specification, but you can use this $50 microphone also.
And the B&K is now DPA, isn't it?
Yeah, it is.
Well, there is still B&K.
Yeah. So
The
some of the
DPA
measurement stuff is still cold.
Yeah, but it's the same mic.
Yeah.
The 4007 is the test mic that I think we use a lot.
Yeah.
The DPA 4007, same mic. They just split divisions. And what's nice about the Earthworks and B&K is that they show you a graph of the response of the microphone. So maybe it's a half a dB swelling up after 5K. So when your measurement shows you that and you don't think you're hearing it, then you know.
So anyway, pretty cool thing. $150 for fuzz measure software. I'm not here to do a fuzz measure commercial, believe me, but it's a pretty cool program. There's also a PC program called ETF, I believe, that is either very inexpensive or free. And the guy who makes that, another very smart guy. And all you need is a decent front end box, a good quality measurement style microphone, small diaphragm Omni microphone. Okay, otherwise your microphone's going to come into play. A lot of these packages actually allow you to calibrate to the microphone. If you can get the data from the microphone manufacturer, you can type in a calibration table, and you'll then have even corrections for the little dips in the frequency response of the mic. You can always go out and buy a calibrator. You can just go crazy. Because we just spend thousands of dollars on this stuff because we love it, and
There's a program. It's a 12-step.
We are trying to get better.
Eventually, we'll probably all be sharing those. But this program does allow you to calibrate. By the way, Fran, did you find that in there?
Yeah.
It's
I
cool.
haven't done it yet, but yeah, Acoustics Anonymous, I think it is. But this program, we talked earlier. I'm going to wrap it up here, and then we're going to go to the Q&A. We talked earlier, and Wes started the whole thing about thinking about energy, time, frequency. Easy to look at two of these things. A little bit more complicated to look at three, just because you're trying to look at three things at once. The classic display that probably everybody's seen a lot it's called a waterfall display. This wonderful, inexpensive program does waterfalls very, very easily. You just go in and you press waterfall. I can't tell you how hard this is to do on the TEF. You got to do, if you want to have 50 time slices, you have to do 50 measurements. But this thing does it very elegantly. Let's get some of this stuff out of the way here. We were trying to figure out how to make a cool, useful looking waterfall before. First of all, you probably want to look at more than 50 milliseconds. You probably want to look at more like 500. We probably don't need to look all the way up to 20K, so I'm going to limit this to 1K because we're really talking about low frequency decay. And then let's crank up the resolution to what their high resolution is. And now we're starting to see, let's see.
Magnitude.
You've got magnitude on the vertical axis here, you've got frequency from 20 to 1K on the horizontal axis, and in the Z-axis coming out of the screen, you've got time. So this is 0 milliseconds, and this is 500 milliseconds down here. You can see up here somewhere around 45, 50 hertz, there's a pretty big peak that's ringing long in this room. That would be something that we as acousticians would want to address. Also up here, oh, that might even be a harmonic of that, maybe, maybe not, 75, 80 hertz, another ring. And then they start to die off. I think this stuff here at the end of the display is noise. I think it's a limitation of, you know, my inexpensive package we're running here. I don't think the 20 hertz is coming back up. Chris and I could argue about that. But, you know, it's probably the fact that there's so much noise in the room. As the measurement starts to decay, we get into the noise floor of the room.
Air conditioning.
Air conditioning, everything, you know. And you expect, the thing that's useful about waterfalls is really to look at low frequency decays in the room. For me, this is the thing that we always want to see. You know, you'll see a low frequency response in a room sometimes, and you'll say, oh, well, what's causing this bump here at
75.
You know, what's causing this bump here? A good way to confirm that it's not necessarily, well, it could be modal, it could be a lot of things. If that frequency is ringing long in the room, good chances are that this is something acoustic. It's not the speaker response. You know, the speaker isn't lasting longer by design. The room's lasting longer by design.
Why don't you show that against the waterfall again? Because those little bumps correlate quite nicely.
No, I can't find the waterfall again. I moved it. See, it's gone. The whole thing. I'm totally screwed. There it is.
So there you got 45 and 100-ish or 80. And when you look back at your frequency response, you can see that it correlates with those.
And now you want me to flash back to that other screen?
Yeah, there it is. Right?
Yeah.
So and even things that kind of look insignificant on a frequency response, but you can hear that it is annoying, or you know there's some ringing. It makes it very easy to see those kind of things on the waterfall because it tells you the time and frequency, and you can see these ridges that often relates to modal setup in the room. And if that isn't treated properly, then they will continue for a much longer time.
You maybe remember your microphone or your head may be sitting in a place where we don't see a peak at that frequency. Move that microphone 3 feet, this low frequency measurement is going to look completely different. This is something really important, I think, a basic concept is that, you know, you don't mix with your head in a vise. You know, it's really cool if you could place the mic and put your head in the vise and say, okay, I know what it sounds like right here, but nobody works like that. And when you do this to adjust something, maybe even an EQ, you've completely changed your relationship with the room and all these comb filters and all this other stuff that's messing with the frequency response. And I think our brain has just gotten really good at kind of averaging all this out. So, you know, especially people who are trained to listen, people who have good ears, you don't get stuck up in the fact that it really does sound a lot different here than it sounds here. It's completely normal. I can even hear it in my voice as I move around that it sounds different. Reflection off the computer, reflections off this. If we move that mic 3 inches, the top end's going to look completely different because that's all caused by reflections off other things, and that time relation differences between the direct signal and the reflected signal change. Comb filter moves. You can't get too caught up with what especially low frequency looks like in one spot. You almost have to move around a little bit. We always start at the armrest of the console and in the middle, and we work, and if we get really stuck on some low frequency thing, we've probably moved the speaker around a little bit already. Like, let's move the mic, you know, move the mic a foot back. It might look totally different. So this is part of I think the experience factor in making these measurements is I can't tell you when to or how much to move the mic. It's an experience thing that we have from doing it thousands of times, literally. But I do think that you can get a lot of information out of these programs, and you know, maybe you get enough information just to say, okay, well, I know there's a problem and I know it's here. Now I'm going to call Chris and I'm going to call Wes. I'm going to get some help on this. We do like to think that you guys should feel like you can call us. You know, we'd rather design your $5 million facility, but you know, if we can't do that today, we'll do the $500 console and try to help you out with your other problems. So hopefully you've all been taking lots of notes. I have. We can get into the question part.
You know, I just want to make, before you go off that, Fran, one thing that's important is what Fran's talking about is how, you know, you might get a reflection here there, move the mic a little bit. Understanding how these things work in real life. I can't tell you how many clients have been looking over my shoulder and they're going like, what's that 2.5 dB at 400 hertz? And it's like, well, it's actually really not there. Well, what do you mean it's not there? I'm looking at it. It's like, I can make it go away. Would you like, I'm looking at it because I want to see what it is. But if you have experience, you can make these graphs look kind of how you want. Just by, I mean, if you're after that. But it's important to realize, like, you're looking at this frequency response, and in the impulse response, the waterfall, like Fran said, if he moves that thing, the top end will change, but you're in the ball game, right? You're in the ball game of that, and you can just change the resolution. This thing will also do show you phase, won't it?
Yeah, well.
Want to show us?
Sure, Chris, I'd love to show you.
Well, that's kind of interesting. See what happened there? Just as he moved in the impulse response, the frequency response adjusted.
It's going to showing me kind of instantaneous. It's showing me the frequency response of whatever window I'm allowing it to look at.
Now, that's very cool. You can see...
That is a slice of the waterfall.
Exactly. That's what you're looking at, is a slice of the waterfall.
Now, that's pretty useful stuff to tell you what's happening in the room, too. Except what?
Numbers along the bottom. As in, like, as you're pulling that to the right, it shows a smaller and smaller.
We're going through time, though, so those numbers don't change.
Yeah, the thing on the bottom is the decay time of the energy broadband, and it's showing you what's happening in the frequency there as we go up.
So now, please understand that this isn't valid below 100 hertz here, because I've got such a small window that I'm looking at. I don't have any valid information below 100 hertz. That's why I got to open the window up to start to get valid information at low frequencies.
All this information we're looking at here was generated from what, like a sustained pink noise burst?
No, it's a sweep.
That one's a sweep.
From that.
Okay.
I was going to do it with my mouth, but that was cooler.
And you can see the
If
low
the mic was
frequency.
plugged in, we can now look at what that. I just did another measurement right there. So my head's in front of the speaker. That can't be good. There's at least a couple of other things between me and the microphone. That's the test I just did. You wanted to see phase, view.
Yeah.
So how does the length of the sweep affect it?
Typically, the length of the sweep, the longer the sweep, the more low frequency information and resolution I'm going to get. That's typical answer to any energy time measurement. My empirical tests on this show that there isn't a lot of difference. So I don't know what kind of transform they're using to convert the impulse. They're doing some kind of fast Fourier transform, but whatever they're doing, I know on the TEF we do much longer sweeps to measure the low frequency part. When we do the TEF frequency measurements, we do two tests. You can see a low frequency test very clearly here, and you can see a high frequency test. This low frequency test was 15-second sweep. This was a 4-second sweep or a 5-second sweep. So if you didn't have that longer sweep on the low frequency, we'd have no resolution. We'd have 50 hertz resolution, so we just see like this. So I had to get down to 5 hertz resolution, I had to open up the time window and do a much longer sweep to get resolution like that. I don't have a good answer for you why it doesn't seem to make a big difference on fuzz measure. Do you have any theories, Lars?
Not really.
Because this kind of resolution that we're seeing down here, it's not stated anywhere what the resolution is. It doesn't tell us.
But again, we know that, we don't have, that level of 15 hertz in this room.
There's nothing
So,
there,
there is a lot of noise that comes into the measurement. And the
Yeah.
longer sweep also will help you make sure that it's listening to this tone for a long time, and random noise won't be that important in interfering with the measurement at that point.
I'll overlay, my head's in a different place, I'm sure, but I'll overlay a long sweep. You can talk during this stuff theoretically too, because, I don't know, this doesn't have a sweat filter, does it? So that was a 10-second sweep versus a 1-second sweep a minute ago. Let's see what kind of difference it makes. And that should be both of them. So that's the difference.
Very
Between
little.
100 hertz, there's a little bit, and like Fran said, his head was in a different place, so
Yeah.
I see a little bit of difference.
You would
on
like to think we had
2K.
better resolution down there below 100 hertz, but I don't know.
It's looking close.
It's pretty darn close.
I think your phase is either in view or in window, maybe. Let's see here.
Look at the frequency.
Was it in frequency? Display type?
Phase response?
Try that. There you go.
Yeah, I'm not buying that.
No.
No, that's times
too good.
100K. Yes, I am buying that actually. If that's
It's
100,000 degrees of
Oh, yeah,
phase.
I'll go back to that again. On display type.
Display type up to the top.
Yeah, I know. I think I checked it. Look at it, something else, guys.
There's it.
There you
Yeah, the minimum phase is.
That's not what you want it to be.
Look at group delay. That's also really important information. You know, when you see these phase responses that are flipped 360 degrees, and you get a little freaked out, the group delay is really important to realize how much discrepancy there is in the time arrival and how it's affecting. So that's pretty good
Yeah,
response.
none of this information down here below 20 hertz means anything, so you can forget about that. I don't even know if it really means a lot below 40 hertz, but
Probably not. Now, the one that you took, the blue one, is the first one or the second one?
blue one's the long one.
The long one, yeah.
And the group delay also relates to what type of speaker it is, if it is a closed cabinet, or if it's a bass reflex, or if it is a passive radiator. The sharper the roll-off on any filter, the more group delay you will have. So, you know, there are several things that will affect this, but it is an interesting view.
Just so you guys know, you got 15 minutes left on the scheduled time. So
Questions?
Yeah,
Keep them coming? Yes.
Sorry, just to be, are you always using sweeps for all this sort of analysis?
No,
I
smarts-
always understood that pink noise was.
Pink noise is the classic excitement signal to use for a real-time analyzer, right? So on Smart, it's almost a source-independent test. As long as you've got some kind of an exciting signal that's got full bandwidth information, all Smart's doing is comparing the output of the sound box to the signal at the microphone. So you can do Smart with music.
That's right.
And it
In real
works
time.
quite well if you've got music that's got broadband, full band.
That sounds like pink noise.
That sounds like pink noise.
In terms of usable results, the kind of thing that actually helps you make decisions about a room, do you find it more useful to work from a sweep?
It's-
it really doesn't matter.
These are the
It doesn't
signals.
matter.
These are the signals that these particular software want to see. Okay, these ETF type programs are looking at swept signs because that's how they work. Pink noise would not work with these programs. Smart. You can look at a bunch of different types of signals with Smart. When it does the impulse response, it prefers to look at a swept sign.
Yeah, it can do
Same thing.
sweeps, yeah.
The original TEF, I believe, was using swept sine waves.
Yeah.
So that sort of became the
Like a
traditional.
classic, like Melissa and those sort of things, they use bursts of like.
Melissa uses an
wavelengths.
MLS signal, which is something else. Yeah.
Yeah. Which
Maximum
is a-
length sequence is what MLS stands for. So.
It is actually a pink noise that is, or it sounds like pink noise, but if you listen to it a long time, you will hear that it actually repeats. It goes, you hear these things in the MLS signal.
Or you can just hire Lars to come over and
He makes
But what you will find is that all these are pretty. They'll correlate well with each other. You do your transfer function with Smart, and then you look at fuzz measure or TEF, or I don't know how some of these other ones. I have seen programs that are out to lunch.
Absolutely, they're not all good.
So
the
be
ones
careful
I
of
mentioned, I
those.
know are good. So.
Well, these three, I'm comfortable using any of these three because I've seen them respond to each other plus or minus a half a dB here or there.
And I concur 100%.
So, some of these other things, I keep getting these things emailed to me with these free software packages trying to get me into some chat group or something, and I plug it in and I try it, and it looks nothing like anything that I'm measuring with any of these other softwares. So,
Are you a Sexy Acoustics 27?
was that you? See, Fran's one of these guys who puts a different picture up. So look out for him.
What was your question?
Yeah, that.
I like the high heels, though, by the way.
We were talking about Jeff earlier. Is that true with all shapes of diffusers or just
I was
polys?
going to ask the same thing.
Well, what we found over probably the past 5 or 6 years of sort of continued development of sound diffusion devices is from the original, like one of the original devices that came out 50 years ago. Manfred Schroeder wrote some really wonderful research papers on it, or the quadratic diffusers called quadratic residue, a primitive root. These devices are very good at they're very good at they're symmetrical, and that symmetry is part of what that in the depths of the wells is part of what that device relies on to be able to scatter the sound.
Right.
But as you add those, next to each other, they're pretty good at minimizing the lobing, but you get it. So it depends on the device. What the research has shown now is what you want to avoid is symmetry to the best of that you can with a diffusion device, symmetry and periodicity. Now, that doesn't go to say that, from a stereo mix position, you don't want symmetry from the center of the room outward. What you're trying to avoid is repeating, the periodicity of it and having symmetrical devices. That when we can minimize that, you get a much improved diffusion coefficient, much improved quality of the sound coming off that surface. The worst offenders are the ones that are the most symmetrical and the most, what would be the most sort of uniform and periodic. Things like arcs or any repeating shape, steady shape like that. When you get up to 4 to 6 of them in a row, the diffusion coefficient just nosedives. And that's new information, which has been leading people to research that more and start to push toward, we've spent years developing it's actually still in development, the diffusion coefficient and becoming an ISO standard. And then the scattering coefficient. Now that the concept of this array, the diffusion array coefficient, is something that's going to be the next one sort of coming up on the test bench.
Oh, I have a kind of question for you that I think will carry on to the question you was asking, which you mentioned about arcs, and when you take a bunch of arcs, the same arcs, you have less and less diffusion, but your waveform system, which really kind of is arcs, but they're varying in size and depth, and that has the potential and the capability of creating diffusion in an arc form when you line them up, much like what your foam has up here, where you don't see the same size arc happening. You've got these waves of different. You want to talk a little bit about that?
Well, the waves. There's new ways of topologies of surfaces that can affect that. You can manipulate the phase to be able for it to scatter. Basically, that's what's happening. That's why something, that's 4 inches deep can actually diffuse a wave that's probably at 18 to 20 inches long, a sound wave. It's because of the phase relationships. It's not because, otherwise it would take, if it was kind of a random surface, you'd have to get a lot deeper with that. You'd have to get to 6 or 8 or I think half wavelength even to be able to start to try to manipulate a wave that's lower in frequency. So the whole goal of it is really to be able to take something that's 4, 6, or 10 inches deep and be able to start diffusing waves down that are this long, and it takes those phase relationships. So with the curves, we're able to do it now with curves. But when you look at them, you'll notice that they're not symmetrical, and we're able to array them in a non-periodic manner, so that we're avoiding symmetry and we're avoiding periodicity with those waves. So it's not like arcs. It's not like a repeating pattern. It's actually something that we can change all the way down. And that actually, when you do that, you can improve the diffusion coefficient. So we're really working on that side of taking something that performs well and then being able to array it such that you get enhanced performance rather than risking degrading the performance of it.
The diffusers behind you, what's their bottom frequency point where they essentially become non-diffusive?
These probably are around 800 hertz. Pretty much on up through. I mean, once you start to get into really high frequencies, you're not really as concerned with as the frequency waves getting smaller, because as the frequency goes up, the waves getting smaller. You're scattering it just because it's a rough surface. Yeah. At that point, it's working. It works pretty much all the way up through. But in diffuser design, what improves the low frequency side of it is actually the dividers that come all the way out to the face. There's different, when you look at different types, this is individual blocks. The types that are on the back have these dividers that create little pockets, and all those dividers, what they do is they help push the diffusion coefficient a little bit lower, make them a little bit more efficient in the lower frequencies.
So what frequency would that be?
Those are about the same.
800.
Yeah.
And that's only 4
But they're
inches
shorter, and these are
And those
8
are 4 inches.
Could you
Now the
take-
difference is you're going to find a little bit in the diffusion coefficient as you get up into the sort of the meat and potatoes of both of them, because this is 156 unique block heights, and that's 4. It's 4, 7, a lot less. So
Significant.
think of it in terms of resolution of how you're breaking up all the different phase cancellations and that you're getting out of this versus something that has a lot less elements.
Yes.
When you guys were talking about the alternative softwares and things that are a little cheaper, is there like a alternative, like a working man's ease or something?
A working man's.
Ease, like something like ease but cheaper? Or
I don't know. Does anybody aware of any? If there is, let me know. But no, I don't.
ETF.
No, but
That doesn't really do it.
it's not the same thing.
No, I think you're stuck.
Well, just so everybody knows, when you get into something like ease, you're really getting into that's something that's focused more on large spaces.
You wouldn't use that for a control room.
Yeah.
They only go down, the large space modeling programs really only go down to about 125. The lowest band is 125 hertz. And a lot of the battle in what goes into the meat and potatoes of design is really how to deal with low frequency resonance in the room, because you're boxing this in and causing this space to resonate and cause interference.
Yeah. Low frequency is the hard part in our business. The rest of it's fairly easy. Yes.
In your general control room, do you have a hard and fast rule of where I put dispersion versus absorption?
That's in Wes's thing tomorrow.
Yeah, actually, we are going to talk about that quite a bit tomorrow.
Yes, the answer is yes.
The answer is yes.
Yes, come tomorrow.
Yeah, what time? What time is that tomorrow?
Actually, same time tomorrow. We're having another acoustics workshop. It's going to be downstairs, Galleria. So it's on the 3rd floor. More in the action. It's this room's going to become a speaker demo room. And it's going to be really cool because Fran's got his speakers here. Chris has his signature series speakers. We've got a lot of other.
We haven't set up yet.
A whole bunch of different speaker brands that you'd probably be interested in hearing. And there's going to be an API 16-channel 1608 console in here. So for the rest of the week, all that stuff's going to be set up here. So tomorrow's acoustics workshop downstairs, and we'll get into a lot more. And I wanted to point out one thing also as far as measurement devices that a lot of people haven't gone. Obviously, a lot of you guys haven't gone into this stuff. Maybe some of you have, but I think what's very useful for a lot of people in their control room as they're learning the control room is some simple acoustic measurement devices. First and foremost, your ears. Secondly, a calculator, maybe a piano or a guitar, so you can figure out what notes you're hearing, and some sine waves or whatever. But sitting there, when we do these measurements in a control room, like Chris was saying a few minutes ago, you can make these windows, you can adjust the gate times and things like that, and you can make these graphs change, believe me. And that's why it takes an experienced, measurer to actually make sense out of them. But what we try to do is we try to find those graphs that correlate with things we're actually hearing. And then when you see bingo, you've got the bump on the graph, it's exactly at 43 hertz, exactly where the speaker's sounding funny, then you go, okay, we really have to zero in on this. Because otherwise, there's so many bumps on those graphs that you can really spin your wheels, waste a lot of time. So I really recommend you become familiar with, what note is 40 hertz. Know what that is. When you listen to your favorite CDs, know what key you're in. So when the bass starts to drop out, that F is always too loud on this song because of where I'm sitting and whatever, and that's X hertz and so on. Knowing that sort of stuff on a gut level, then moving into some of this fancier software, I think is the way to go.
For those guys who don't know, Wes is the guy who talks about modes in terms of musical notes. So he's all about
trying to keep it real, keep it in the musical realm.
Keeping it real.
So the quick, easy way to do that would this be an accurate way to do it? Just plug like a keyboard into your studio monitors and sit there and play up the spectrum?
Yes.
Sure.
Yes. Also, find out, take a calculator. If A is 440, it's also 220, 110, 55. So no, when you're thinking 55 hertz, think A. Start thinking of them that way. Instead of just talking about 250 is a muddy region, whatever. What note is that? It's middle C,
On the Mac, there's actually a couple of widgets that
you press comes up and it'll give you a keyboard and tell you exactly what frequency you just hit the keyboard.
That's cool. So those kind of tools are really useful for you as you try to make this actually relate to your mixing abilities.
If you do a search for note to frequency chart, you'll find any number of things too.
Yeah.
Mac has another widget that's really cool also. It'll tell you how long a wavelength is. You can type in a frequency, it'll tell you how long it is. And another thing that's a really great tool, headphones. Get a good reliable set of headphones like some Grados or something. And if you're hearing an anomaly in your control room, that might be hanging out there, you can put on a set of headphones and you can eliminate room that way. Of course, you want to know that your headphones aren't out to lunch. Get some reliable. Grados are great. There's some other ones out there as well.
No iPod earbuds.
No earbuds allowed.
Excuse for your room not sounding right.
More questions?
Anything else?
Go ahead.
When I used to run sound for bands, I'd shoo everybody out and do a pink noise with an RTA. I always read that you're supposed to go like 3 dB slope after 1K.
Some people like that. You know, I have had clients who prefer a little roll off like that, and I have others like mastering guys who say no, give it all. It's what they're used to listening to.
You want to know where I think that comes from? I think that comes from a lot of the horns that were used in live sound systems. They just get really beamy as you get up into the 4, 5, 6 and higher area. So a nice roll off, 3 dBs per octave, kept that under control. It kept the system from just sounding, tearing your head off is what it came down to.
When we're using
That's right.
studio monitors, it's not applicable.
I used to be a big believer in it. Once again, when we were using compression drivers and horn-loaded systems, these days, I'll take that information all the way out, please.
I'll agree with Fran on that as well. I like to see it all as close to.
I don't want to hear an 813 flat out to 20K. No, thank you. But our speakers, yeah, I'd like to hear them flat out to 20-something K. It's all good stuff. Anybody else?
How does the level that you mix at affect the frequency response?
Who wants to talk about Fletcher Munson?
You?
Go after it.
The natural loudness curves that two guys came up with, Fletcher and Munson, I think, or else his name was Fletcher Munson.
I think it was Munson Fletcher.
Yeah. So the louder you listen, the more emphasis you hear on both low frequency and high frequency, right? That's why it sounds better loud, guys, because your ears work like that. It sounds.
You have a chart of that, Chris?
Do you have a Fletcher Munson curve?
I don't.
Yeah, I don't have any.
No.
There's, if I may, I add a little bit. I think the whole Dolby standard of listening levels has addressed that. They find that, you know, around 75, 80 dB, the hearing is comfortable, it's loud enough, and you can have dynamics that goes up above that. But it is part of the Dolby philosophy is also that, you know, it should be, when you set that level in the mixing room and in everywhere you hear it, it is you have the same perception of the low frequency and the high frequency in relationship to the mid frequencies wherever you go. And so I think that part is also baked into the Dolby thing, and I think that type of listening level is probably where your hearing is, should we say, most accurate.
What's that, 85?
Yeah, 75, 85 in that range.
And keeps you working for without getting fatigued.
I can talk a little bit real quick on that. That also depends on how big a room you're in and how close you are. And, you know, what we've discovered doing a bunch of stuff for Sony is that in the smaller rooms, and there's a lot of controversy out there, 78 dB, some people say 80, 85. One thing that occurs depending on what you're listening, if you have a speaker that is particularly harsh or has a lot of distortion, your brain's going to start to, or really inaccurate phase information, your brain will start to shut down, and the louder you listen to that, they call it ear fatigue, but what it really is your brain saying, I don't want to try to figure this out anymore. And you keep turning it up, and it keeps shutting you down, your ears can compress. So I would say listen, 85 to me, and this is a real, we could open this discussion, we could beer it till tomorrow, but I think 85 is like at the top of where I would mix on a long period of time. I crank it up sometimes to 100 just for a second, but I'm usually down in the 70s when I'm mixing.
If I could add one thing to that, the Fletcher Munson curve, what they found out is that at low levels, let's say down around 50 or 60 or whatever, your ears actually have the opposite of a loudness contour curve. They're dropping off in the low end, they're dropping off in the high end, and you're hearing things very mid-rangey. That's why they used to put a loudness button on receivers back in the 70s. It was when you're listening low at night, and it's very soft, you're trying to not disturb the wife, it restores the highs and the lows and puts that smiley curve on there, which theoretically flattens it back out.
We just have more sensitivity in the mid range for lower levels.
For lower
because
levels.
It's survival. It was all about hearing the thing that was coming to eat you when you were.
So you don't want to listen super soft either to make your mixes.
Yeah.
If you make mixes really soft, you'll make mistakes.
Really big in the bottom and the top.
Exactly.
That's true, yeah.
You don't want to mix too loud or too soft.
I just wanted to say a couple things about the loudness things. One, THD's hot plates have that same thing in them. As you turn them down, they naturally push the lows and the highs back up, just like the loudness button. Another thing, though, like you were just saying about mixing super low, there's some people that do that on purpose, and it's like it will result in everything is the exact same volume mix. It'll sound like it's been mastered, squashed. As in, you won't mix in dynamics because you can't hear anything quiet.
Mhm.
Right.
So you'll mix.
Dynamically,
some
you're
people think
exactly
it's really
right.
cool, and it's just
I think you'll also end up with hyped bottom and top.
Right.
That's my experience. When I used to do this and would make a conscious effort to listen really soft all night because I was working with that kind of guy or whatever it was, and then I listened to it the next day. Holy cow! That's
Well, you get used to also.
Now, I absolutely recommend listening really soft when you're cutting vocals or comping vocal tracks because your ears are much more sensitive to intonation. If you comp a vocal nice and softly and then do another one the next day kind of loud and listen to the work you did, your intonation, a lot of times the clients won't hear, what are you talking about? She's flat there. Well, turn it down and play it for me again. They go, oh, you're right. It's really flat.
If any of you guys are out playing live too, I do a bit of that, and I'm always hammering the monitor mixer because he's just cranking. I'm like, I can't hear anything. You got to turn it down. Those days of like super loud and making your ears bleed, it's not happening. It's bad for you.
I was just going to say that the loudness curve supposedly is because our ear is, most people's ear is like 2 inches long, is that right or something? So it resonates, it's a pipe that resonates at 3K. That's why 3K, when you turn it up, when you mix, it's like, wow, it sounds loud as hell.
I don't know if that's...
Here you go. Did you have
I've also, and I don't know if there's anything that backs this up, but I also noticed that in headphones, my pitch perception isn't as good. Is there some reason I'm separating the
Have you ever noticed when you take off the headphones how you get the Doppler effect?
Yeah.
Yeah, I absolutely agree. You can't really be. It's not
Like
necessarily
trying to do,
reliable.
like your example of comping vocals. and doing
Don't try to
anything
tune a bass with headphones on.
I think the reason that is you've concealed the air pressure, and your ear needs to move like a speaker. When you've cupped that in, there's going to be some deviation in the way that your eardrum actually.
I think vocalists sing more in tune if you can figure out a way to record with speakers.
Well, that's exactly
much.
what I've
Yeah.
done it, but putting speakers out of phase and
You
using
sing a lot
bidirectional
more in
mic
tune.
and-
Yep.
Yeah.
Put one off. You've seen it, even now they got headphones where it's only one. That allows your other ear to. That's why playing live, these guys like these in-ear things, and I don't like them. But
No, it makes the soundman's job easier, right? Makes everybody
Feedback.
Yeah.
it makes a lot of things easier, but I haven't been able to get used to them.
Yeah.
I'm just.
Anybody else with a question?
I have a question about when you're starting from scratch with design. This is all basically once the room is pretty much done, and then you're trying to figure out what you still need to work with. When you're starting from scratch, basically you're dealing with modeling then, right? Like there's nothing like this you're going to do as you're going along until you're pretty much done.
That's a whole panel that we aren't really.
Well, you might want to make noise tests at the beginning of
As
the
you're
building. Well, just at the raw building. You need to
Oh,
know
okay.
what
Background's gonna resonate.
NC test.
Yeah.
NC
Yeah,
test.
but most of us are going to be designing rooms that aren't going to have reflection problems, so we don't have to go and test to make sure that we don't have console reflection. We've taken care of that.
Okay.
RPG makes a product now. If you're starting from scratch, which typically we do, you got a big open building or even an outdoor area, and you're starting to build. There's relationships between height, width, and depth that will give you. You have something to show for me?
I'm hoping I do.
Yeah.
But this is a Mac, so I don't know.
That will show
Optimizer?
how to get the best low frequency response in just a regular enclosure. It makes it a little easier to treat it that way.
This is a great program, guys.
I'm going to let Jeff demonstrate.
Actually, can you pull
And then once you have that enclosure, height, width, and depth, then you can take it from there with the bass control and mid-range diffusion, etc. I really like this program. I used to, now I got to tell you, I used to do this by hand, and it would take me, Wes was laughing today, because sometimes it would take me 2 to 3 weeks, because you have to calculate the harmonic structure of each dimension. And when they
iterations there, he had to do one at a time.
Yeah, the
Yeah.
computer. Oh, Jesus Christ! Let's fix that. The computer just did 600 iterations of different room dimensions. So poor
600 or more than that.
600, it looks like. So poor Chris was there doing calculations for 3 days to get 50.
Yeah. Yeah, and the funny thing is you get it just about right, and then one harmonic collides right where you don't want it. You got to go back. Then you move that dimension, and it changes and interacts with another dimension. So these computer programs are absolute lifesavers.
That's why God gave us computers.
Jeff, explain this.
What the room sizer does is it uses an iterative sequence to they call it's a downward iteration that tries different room dimensions, width, length, and height. It tries it. It compares it against a metric that's already really programmed into it, but that you can set where you would like the room to be, and it smartly takes that and says, all right, that one wasn't so good. I'm going to go this direction and try this way. And so what it's really good at doing is starting from scratch, saying you've got a space that you say, I think I want the control room to be about 18 feet long by 16 feet wide by 10 feet tall or something. And that's how much maximum room you have. But maybe you're willing to let it be, 17 by 14 by 9. So you plug in a minimum. I don't want my room any smaller than this. And you plug in a maximum. This is as big as I can make it. And this program will actually find really good height, width, length, dimensions, ratios for you. There's a lot of ways to, like these guys were saying, a lot of people have done this by scratch with spreadsheets, and there's a lot of published ratios out there. There's a lot of research on room dimensions. The problem with a lot of them, what you have to be careful for is those ratios. There is no golden ratio. It doesn't exist, because that ratio, that golden ratio, changes when the volume of the room changes. So you might find the golden ratio for a room that's 16 by 12 by 8, but that's not the golden ratio for a room that's 18 by 15 by 10. That has a different optimum ratio. And there's ways of finding that. This is just an easy way. And so what you get is, it gives you it basically shows you everything that it's done, and it shows you the worst value that it happened to find, and then the best value that it happened to find. And it gives you, really all it does is it just gives you a good place to start, because there's a lot of work from that to do, but it gives you kind of a way to start with a pretty good footprint of the room.
Explain the coincidences there. Is that's what it's showing you, is what frequencies are kind of landing on top of each other? What are those?
The numbers on the top are those are the modes.
Yeah,
so the very first one that says, looks like 100. What that is that's axial, tangential,
First,
and
There's a 3 dimensions.
It's your longest. Your
100
longest.
is just the length. The 010 will be the width of the room, and the 001 will be the height of the room.
Yeah.
And then you
So
have
110
combinations
is
of
a
that.
tangential.
1 means that it's the first. That's the fundamental. So that you can see from the length of the room and that's just showing you where all of those land. So you can see where all of the different combinations land.
And also where you have several numbers, it means that, where there's 2 numbers, it means that it travels between 4 walls. Where there are 3 numbers, it actually bounces on all surfaces in your room.
Yep.
I have one other question, because I have run a few of these and stuff. I haven't run this one. I like that. What happens when you start putting more than, like these are all based on a rectangle or a square? What happens when you start doing that? All this goes kind of out the window.
All bets are off.
Okay.
What that requires, real quick, what this is doing is this is taking the wave equation, and it's calculating. You can compare this to real room measurements, and they nearly overlay perfectly. It's a real.
I reviewed your software, the RPG software for Mix Magazine 10 years ago.
Yeah, I read that.
Okay.
And it was dead on.
If we look at this window, you see it says listener and loudspeaker. If you were to the conditions where this software will give you a perfect overlay with this response is when you place the loudspeaker in the lower corner and the microphone up in the diagonal top corner. That's when you excite all the modes in the room and you pick them up perfectly. That's, just wanted to explain.
That's what it's modeled. That's
If I
what
could
it's
just make
modeled.
I just want to make one comment about this. I use this software a lot, and I think it's great. It's one of the greatest pieces of software ever written. But it does not think for you.
No.
And you can't just, otherwise, they wouldn't bother putting out the software. They'd say, well, here's the perfect room. Go build it. Because you have to be careful. The computer will, if you give it some criteria, say, it allows you to put in certain constraints. Let's say the speakers must be against the front wall for some reason. You can say that. Or you can say, no constraints. You just tell me with this room, what to do. But let's say you give it constraints. It can come back with a worst case, best case scenario like that and say, well, the best case is with you sitting, 49% of the way between the front and the back wall, which is dangerously close to 50%. And 50% is awful. The computer doesn't really distinguish there, okay? Well, I would never place the listener there because when you lean up this much, now the computer is a great tool used in combination with your own common sense and experience.
Does everybody understand what we're talking about when we talk about your initial? There might be some people that don't understand the whole idea of the tonic frequency and the harmonics of each of these dimensions and how they interact with each other as the frequency rises. Does anybody need a better explanation of that?
When you said tonic, is that?
The fundamental.
Okay.
The root tonic, that's like a musical thing,
Yeah.
The root frequency, the lowest frequency of that particular dimension.
You take half the speed of sound and divide it by let's say, half the speed of sound is 565. Okay, divide it by 20 feet, let's say here. That's going to give you the frequency. It's going to be about 25 hertz or so. That's going to be the fundamental frequency for this mode. It might be closer to 20 hertz here because we're a little deeper. And then you're going to get harmonics at all the natural numbers of that. So you're going to get 25 hertz, 50, 75, 100. And
Understood. I just didn't know if tonic was something I hadn't heard of.
No.
Tonic goes well with gin as well. Yes.
I felt that coming from Fran.
Are there naturally occurring subharmonics? I mean, I always wonder about that.
No, if you have 25 hertz in that situation, that's the only tone. You won't start to hear 50 and those harmonics. It's only that one.
Which is why you don't want to have a room that's 20 by 10 because 10's tonic is going to be 50 roughly, and
yes, even multiple is always bad.
Yeah, and that's where you get huge suckouts or augmentations of frequencies. So you walk through some rooms, you go, wow, it's really big bass. Oh, there's no bass, and you're moving around.
That's still a problem with stuff like not even direct ones, like 10-15 is still a bad idea, right?
Mm-hmm.
It's still both by 5?
Yes.
Yep.
Actually, if the room is open, the room that this was supposed to be in, the Oakley room, the reason we moved it was because it must have been right next to a mechanical, like a HVAC.
Yeah.
God,
It sounded like there was a subwoofer thumping in there.
I thought somebody had a subwoofer running in the room in the corner doing a test or something when I first walked in. It was incredibly loud. I mean, unusable, completely unusable.
We were going to do the acoustic tests in there.
Yeah, we were going to say.
You guys wouldn't
try
have
to
been able to
battle
sit in that room this long without getting sick.
If you go in that room, if it happens to be open, because we're going to be down right next to it tomorrow on a panel, if it happens to be open, walk in there because you'll walk around the room and you'll find spots where that noise goes away completely.
Yep.
So it gives you kind of a feel for that cancellation of how the room works because it's the room itself, like a string on a guitar. It's the room itself resonating and supporting different.
One more step with this too, because I hear this from a lot of phone calls. The guy goes, "Oh, I turn my oscillator on to 100 hertz and I don't hear anything in the mix position." Mm-hmm. Yeah, but what's your point? So this is physics, guys. I listen to any pure tone in a room out of a loudspeaker, I'm going to walk through natural peaks and valleys. I have to. You can't make that go away. 1K, 2K, 10 hertz, 50 hertz, they're all going to have peaks and valleys. They have to. The science or the math of doing this stuff is about making those peaks and valleys musically relate to each other and not pile up on each other.
That kind of leads me into why we use, porous absorbers and other forms of absorbers in a room. If you had a concrete bunker, there would be a very distinct zero in the middle there wouldn't be any level whatsoever at that frequency. Well, what you introduce when you introduce absorption is you remove the level from the wall surfaces, and it actually comes up in the middle. So it is like adjusting the Q on an equalizer. You're actually inserting resistance into the resistive circuitry, and that's why we treat rooms with different types of base absorbers, to remove some of these very distinct valleys where there's no sound whatsoever.
Yeah, bass traps don't make you get less bass. Another popular misconception. I have
More
too much bass trapping because I've got too many bass. I got not enough bass because I have too many bass traps. Exact opposite. You can't have too many. You can't.
Apart from it will require a lot of output from your speakers at some point.
But we're talking about way too many of that.
You guys really should come if you're interested in this. The panel tomorrow, we're going to be talking a lot about that, and I couldn't agree more with Fran. As long as you put that bass trapping in the right place, you know, you can't have too much.
Ironically, the biggest fear is that you'll lose too much high end from all those bass traps, because they also tend to soak up highs.
That's why we vary between, you know, Helmholtz type of resonators or porous absorbers or, you know, other panel absorbers. We'll mix this up because we do need to make sure that it's an even response throughout the frequency range.
You guys mentioned room geometry, and we were talking about this is just good for rectangular rooms, but most people in here probably know about using the room geometry and the angling of the walls and things of that nature. So how do you, like, I've got a space that's 18.5 by 25 by 8 feet tall. Would it be better just to go with that, or should I build an angled wall in there?
I think that if you're going to get into geometry and you don't have a lot of experience, that you might want to consult with somebody about what you're doing, because it does get a little bit
It's a lot more complicated.
That's my fixed space.
Yeah, and then it is much easier to treat that room afterwards if you find out that, 60 hertz is like ringing forever. It's much easier to treat that if you have started to introduce geometry in the room.
Yeah.
Okay.
So it is a very simple
You can
and
control,
easy
you can
way
control
of
your
just starting
reflections.
with rectangle.
These first reflections that we were hoping to demonstrate controlling today, it was hopeless. You know, you can control these in a rectangular room very easily. Assuming you're not going to build speakers into a wall, which I'm assuming you're not, you know, that kind of dictates that you're going to have a non-rectangular room. As soon as you start to build speakers into the wall, now you've got two walls that are angled, no longer a rectangle, right? So it gets...
And sidewall geometry and all that, I mean, it really does get to where it's very complicated. You're manipulating energy. You better know what you're doing.
And we're not trying to be cagey about this. There's no simple answer.
But see, the problem is when you do stick with rectangular geometry, parallel surfaces, then you've got more parallel surfaces with flutter echoes, and it's easy to overdeaden a room.
It is.
That's why we do some of this flaring, is to redirect reflections without having to absorb them.
Sure.
So you can keep more natural decay times at higher, mid, and higher frequencies. So we're trying to get those low frequency decay times down reasonable without killing the mid and upper decay. We want a fairly smooth decay time across the spectrum.
This type of analysis is useful up to you can go up to about a 2-degree angle in the walls, canting the walls, and it's still overlays very nicely. What you can do, I mean, you know, there is a benefit to doing different kind of designs, both aesthetically and functionally for performance, and you want to do different things. So it's always good to just run what you can and learn what you can about the volume that you're working with, because you could compare if your room is ultimately going to be shaped a little bit different, but it's effectively, you know, if you looked at an average of a certain length by height by width, you can get a characteristic of what to expect the problems might be. It just gets harder to predict. We know what a shoebox does. All from 20 to 20K, we know exactly what it's going to do. It's just easy to predict how to correct it.
When we get into multi-sided rooms beyond parallel rectanguloid shapes, we end up doing these calculations on multiple iterations of what the minimum, maximum, average, mean dimensions are, and it just gets hairy because you can't get them all right. So we have to use our intuition to tell us that which ones are problematic and which problems that the simulations show are not problematic. So there is no it really is, it's an experience thing. It's seeing, having built, you know, a couple of hundred rooms that do have angled walls, now I know what predictions we made came true and what predictions we made were not so true. So it's empirical. That's what it comes down to.
We're sort of like a program. We keep repeating these things until we get it right. And honestly, what you've got, you know, you've got probably 3,000-4,000 rooms between on this panel, and so there's really no easy answer to that question other than become a studio designer and go crazy with the rest of us. We welcome you.
And also these numbers, you know, things that are bounced between several walls, they will have traveled longer distance, so the significance of the level will be less.
That's right.
And all these things we have to juggle around till we find a good solution. So some of them aren't important, and you know, if it's the direct ones, they are significant, and we have to deal with them. And also, in the higher up in frequency, 100, 200 hertz, it's very easy to deal with them with, you know, corner absorbers and stuff like that. It's very easy to get rid of.
Is that it?
Lunchtime.
Thanks for hanging,
coming,
everybody.
Appreciate it.
Thank you.
Thank you.